welcome to my sleep science channel. Before we begin tonight, tell me where in the world you are watching from. Perhaps you are listening beneath a warm blanket after a long day. Perhaps you are watching while rain taps softly against a window. Or perhaps the night outside is perfectly still. Wherever you are, allow your thoughts to slow down as we travel into one of the greatest mysteries ever encountered. It is a mystery so enormous that it stretches across every galaxy, every empty region of space, and every direction the eye could ever imagine. It is called dark energy. And despite filling almost the entire universe, no one has ever seen it directly. Long before anyone imagined dark energy, people believed the universe was simple. The stars appeared fixed above Earth, rising and setting with quiet reliability. Ancient civilizations carefully watched the heavens and noticed patterns that repeated over generations. The night sky seemed permanent, calm, and unchanging. Even after telescopes became powerful enough to reveal distant planets and countless stars, many scientists still imagined the universe as something stable, almost frozen in time. As the centuries passed, better telescopes slowly transformed that comfortable picture. Tiny blurry patches of light that once looked like faint clouds turned out to be enormous galaxies, each containing hundreds of billions of stars. The universe suddenly became unimaginably larger than anyone had expected. Every improvement in technology revealed even greater distances, more galaxies, and deeper layers of the cosmos. Instead of reaching an edge, astronomers found more space waiting beyond every previous limit. Distance itself is difficult for the human mind to appreciate. Walking across a room feels familiar. Driving across a country already seems enormous. Even traveling to the moon takes several days using modern spacecraft. Yet the nearest star beyond our sun is so distant that its light requires more than 4 years to reach us. The nearest large galaxy, Andromeda, lies over 2 million light-years away. Beyond it are millions upon millions of additional galaxies, stretching farther than any telescope can completely observe. When astronomers speak about the observable universe, they are referring only to the part whose light has had enough time to arrive since the beginning of cosmic history. That observable region is already almost beyond imagination. It contains hundreds of billions, perhaps even trillions, of galaxies. Every one of those galaxies contains stars, planets, clouds of gas, dust, black holes, and countless stories that will never be witnessed by human eyes. Despite these staggering numbers, matter itself makes up surprisingly little of everything that exists. The stars lighting the night sky, the planets, the oceans, mountains, trees, animals, and every person who has ever lived belong to a surprisingly small cosmic category. Ordinary matter accounts for only a tiny fraction of the total contents of the universe. Most of reality is hidden from direct observation. For many years, astronomers believed that invisible matter was the greatest mystery. They found convincing evidence that galaxies contained much more mass than telescopes could detect. This unseen material became known as dark matter. It does not shine, reflect light, or glow, yet its gravity helps shape galaxies and galaxy clusters. Dark matter remains mysterious even today, but another discovery eventually appeared that was even more surprising. Imagine standing on a quiet beach as gentle waves roll toward the shore. You throw a ball into the air. Gravity always pulls it back. Every experience in everyday life teaches the same lesson. Gravity attracts. Gravity gathers. Gravity slows things down. Whether it is an apple falling from a tree or planets orbiting the sun, gravity acts as a force that brings objects together. Because gravity always attracts, scientists naturally expected the expanding universe to slow down over time. The galaxies were moving apart because of the tremendous expansion that began billions of years ago. Although they continued separating, gravity should have gradually reduced their speed. It was similar to throwing a ball upward. The ball continues climbing for a while, but gravity steadily removes its speed until it eventually stops and falls back. This expectation seemed so reasonable that very few people questioned it. Entire generations of astronomers built calculations based upon this simple assumption. They argued over exactly how quickly the expansion should slow, but almost nobody doubted that slowing was taking place. Then observations began revealing something astonishing. Instead of slowing down, the universe appeared to be doing exactly the opposite. The farther scientists looked into space, and the farther they looked back into cosmic history, the clearer one remarkable pattern became. The expansion of the universe was speeding up. This discovery did not merely adjust existing theories. It challenged some of the deepest assumptions about how the universe behaves. Something unknown seemed to be overcoming gravity across unimaginably large distances. Something invisible was gently pushing galaxies farther apart, causing space itself to expand faster with the passing of billions of years. That unknown influence became known as dark energy. The name sounds dramatic, but in truth it simply reflects our lack of understanding. It is called dark, not because it is black or shadowy, but because it remains hidden from direct observation. It neither glows nor reflects light, and no instrument has ever captured it in the ordinary sense. Scientists observe only its apparent effects upon the expanding universe. Today, dark energy represents one of the greatest unsolved mysteries in modern astronomy. It appears to dominate the universe, influencing the largest structures that exist while remaining completely invisible. Every galaxy, every cluster of galaxies, and every immense stretch of cosmic emptiness quietly participates in a process driven by something humanity has not yet learned how to explain. The deeper astronomers look into the universe, the more this silent mystery reveals itself, patiently waiting beyond the limits of current understanding. One of the most surprising ideas in modern astronomy is that galaxies are not simply moving through space as ships move across an ocean. Instead, the space between galaxies is itself growing larger. This distinction may seem subtle at first, but it changes the entire picture of how the universe behaves. It suggests that the universe is not expanding into an empty region beyond its edges. Rather, the distances within the universe are gradually increasing, carrying galaxies farther apart as time quietly passes. For thousands of years, people naturally assumed that space was fixed and unchanging. It was thought of as an enormous stage upon which stars, planets, and galaxies moved. The stage itself seemed permanent. Nothing in everyday experience suggested that space could stretch, bend, or grow. A room remains the same size whether someone walks through it or not. A road does not become longer simply because two cars drive away from one another. Human intuition is shaped by life on Earth, where the fabric of space appears perfectly stable. The universe, however, does not always behave according to everyday intuition. On the largest scales imaginable, reality follows rules that seem almost impossible when first encountered. These rules only became visible after astronomers developed instruments capable of observing galaxies far beyond our own. Every improvement in telescope technology extended humanity's vision deeper into the darkness, revealing a cosmos far more dynamic than anyone had expected. One of the most important clues arrived through the study of light. Light is far more than simple brightness. Every beam of starlight carries detailed information about the object that produced it. Hidden within light are patterns that reveal temperature, chemical composition, motion, and distance. By carefully separating light into its different colors, astronomers discovered that stars and galaxies leave unique signatures, almost like fingerprints. No two chemical elements produce exactly the same arrangement of lines within a spectrum. As telescopes collected light from increasingly distant galaxies, astronomers noticed something remarkable. Nearly every distant galaxy displayed the same unusual pattern. The familiar spectral lines appeared shifted slightly toward the red end of the spectrum. This effect became known as redshift. At first glance, it may seem like a minor technical detail, but it became one of the most important discoveries in the history of astronomy. The reason behind redshift is closely related to something most people experience without realizing it. Imagine standing beside a quiet road as an ambulance approaches. The siren sounds slightly higher while it moves toward you. As it passes and drives away, the sound immediately becomes deeper. This familiar change is called the Doppler effect. The sound waves become compressed while approaching and stretched while receding. Light behaves in a similar way. When an object moves away, the wavelengths of its light become longer. Longer wavelengths appear redder. When an object approaches, the wavelengths become slightly shorter, shifting toward blue. By measuring these tiny changes with extraordinary precision, astronomers can determine whether distant galaxies are moving closer or farther away. The observations were astonishing. Almost every galaxy beyond our local neighborhood appeared to be moving away. Even more surprising, the most distant galaxies seemed to be receding faster than nearby ones. At first, this sounded impossible. Why would galaxies in every direction all appear to be fleeing from Earth? It almost suggested that our galaxy occupied the center of everything. But that interpretation quickly proved incorrect. A simple analogy helps make sense of this strange observation. Imagine tiny dots drawn across the surface of an uninflated balloon. Each dot represents a galaxy. As the balloon slowly inflates, every dot moves farther from every other dot. No single dot sits at the center of the expanding surface. From the perspective of any individual dot, every other dot appears to be moving away. The farther apart two dots begin, the faster the distance between them increases as the balloon grows. The universe behaves in a similar way, although the comparison has important limits. Galaxies are not painted onto the surface of a balloon, and the universe is not expanding into surrounding air. The analogy simply illustrates how increasing distances can make every location appear central, without there being an actual center inside the expanding space. This realization transformed astronomy. Instead of imagining galaxies flying outward through a fixed cosmic emptiness, scientists began describing the expansion as the stretching of space itself. Galaxies mostly remain where gravity has placed them locally, while the immense distances separating galaxy clusters gradually increase. The expansion is not like an explosion sending debris outward from one location. It is the quiet enlargement of the cosmic fabric on the grandest possible scale. This expanding picture also explains why extremely distant galaxies appear to move away so rapidly. They are not necessarily traveling through space at extraordinary speeds. Rather, more space exists between us and them every passing moment. As that space stretches, the total distance increases naturally. Over billions of years, even a very gentle rate of expansion produces unimaginably large separations. Closer to home, gravity remains strong enough to resist this expansion. Our solar system is not gradually growing larger because of dark energy. The planets continue orbiting the sun much as they have for billions of years. The Milky Way galaxy also remains intact because its own gravity easily overcomes the incredibly weak stretching of space across relatively small distances. Even our neighboring galaxy, Andromeda, is moving toward us rather than away because gravity dominates the local environment. Only across enormous cosmic scales does the expansion become impossible to ignore. Between distant groups of galaxies, where gravity weakens over immense regions of nearly empty space, the stretching gradually becomes the dominant influence. Entire clusters drift farther apart over billions of years, not because they are actively flying away under their own power, but because the universe quietly creates more space between them. This idea remains one of the most beautiful and peaceful concepts in astronomy. The universe is not rushing chaotically in every direction. Instead, it resembles a vast, silent landscape whose dimensions slowly increase with time. The process unfolds so gradually that no human lifetime could ever notice it directly. Yet across billions of years, this gentle expansion has transformed the cosmos from a hot, dense beginning into the immense universe visible today, setting the stage for the even deeper mystery of why that expansion refuses to slow down. Gravity is the most familiar force in the universe, even though it is also one of the weakest. Every step taken on Earth, every falling leaf, every drop of rain, and every orbiting planet quietly follows its influence. Unlike light or sound, gravity cannot be seen directly. Its presence is known only through its effects. It gently shapes motion, holding worlds together and guiding the paths of stars across the galaxy. On the largest scales imaginable, gravity is the architect of the universe, patiently building structure over billions of years. From the moment the universe began expanding, gravity immediately started working against that expansion. Every atom attracted every other atom. Tiny clouds of matter slowly gathered into larger clouds. Those larger clouds eventually became stars. Stars collected into galaxies, and galaxies assembled into enormous clusters stretching across millions of light years. The universe that appears richly structured today exists largely because gravity never stopped pulling matter together. This attraction is remarkably simple in principle. Every object with mass pulls on every other object with mass. The strength of that pull depends on two things: the amount of mass involved and the distance separating the objects. A nearby mountain pulls on you very slightly. Earth, being vastly more massive, holds you firmly on its surface. The sun, containing almost all the mass in our solar system, keeps every planet traveling along graceful paths that have remained stable for billions of years. Although gravity feels powerful in daily life, it is surprisingly gentle compared with the other fundamental forces of nature. A small refrigerator magnet can easily lift a paperclip despite the combined gravitational pull of the entire Earth beneath it. Yet gravity possesses one remarkable advantage. It never switches off, and it always attracts. Over enormous distances and unimaginably long periods of time, these countless tiny attractions add together until gravity becomes the dominant force, shaping the largest objects in existence. Imagine standing beside a calm lake and tossing a handful of small stones into the water. Each stone creates ripples that spread outward. Now, imagine every star, planet, and galaxy producing an invisible influence that extends endlessly through space. Every object responds to every other object, however distant. The universe becomes an intricate web of attractions, each one almost unimaginably weak on its own, yet collectively responsible for forming galaxies, clusters, and the immense cosmic web that stretches across the observable universe. Because gravity always pulls inward, astronomers naturally expected it to slow the expansion of the universe. This expectation did not require complicated mathematics. It followed directly from everyday experience. Throw a ball into the air, and gravity steadily reduces its speed. Launch a rocket away from Earth, and gravity continuously pulls it backward. Even if the rocket escapes entirely, gravity never disappears. It simply becomes weaker with increasing distance. The expanding universe seemed to follow the same logic. Billions of years ago, everything was much closer together. As space expanded, galaxies began moving apart. Their motion carried them outward, while gravity constantly worked to reduce that outward movement. The expansion might continue forever if enough speed remained, or it might eventually stop and reverse if gravity proved strong enough. These possibilities became central questions in 20th century cosmology. Scientists imagined several different futures. In one possibility, gravity would eventually halt the expansion completely. The universe would stop growing, pause for an instant, and begin collapsing inward. Galaxies would slowly move closer together, temperatures would rise, and the cosmos would end in a dramatic contraction sometimes called the Big Crunch. Another possibility seemed gentler. Perhaps gravity would never completely stop the expansion, but would continue slowing it forever. Galaxies would keep drifting apart, though at an ever-decreasing rate. The universe would become larger with each passing billion years. Yet the pace of expansion would gradually diminish as gravity patiently continued its work. There was even the possibility that the amount of matter in the universe happened to lie exactly on a delicate balance. In that case, gravity would reduce the expansion more and more without ever quite bringing it to a halt. The universe would spend eternity approaching stillness without ever reaching it completely. This idea fascinated many cosmologists because it represented an elegant middle ground between endless expansion and ultimate collapse. All of these predictions shared one assumption: gravity always opposed expansion. The only uncertainty involved how successful gravity would be. Would it win completely, partially, or almost completely? Few researchers seriously considered that something entirely different might be influencing the universe on the largest scales. Meanwhile, gravity continued creating magnificent structures throughout cosmic history. Vast clouds of hydrogen collapsed under their own weight until nuclear fusion ignited their centers, producing the first stars. Those stars manufactured heavier elements before scattering them into space through powerful explosions. New generations of stars formed from this enriched material, eventually giving rise to rocky planets and, much later, living organisms capable of wondering about the universe itself. Entire galaxies also evolved under gravity's careful guidance. Spiral galaxies developed elegant rotating disks filled with glowing stars and dark lanes of dust. Elliptical galaxies formed through ancient mergers, becoming smooth collections of billions of aging stars. Clusters of galaxies, containing hundreds or even thousands of individual galaxies, emerged as gravity slowly assembled larger and larger structures across immense distances, on scales of millions of light years. The universe resembles a gigantic three-dimensional web. Long filaments of galaxies connect enormous clusters, while immense empty regions known as cosmic voids separate these bright strands. Gravity built this extraordinary architecture over billions of years, gradually amplifying tiny differences that existed shortly after the universe began. Without gravity, the cosmos might have remained an almost featureless sea of particles spread evenly through space. Even today, gravity dominates every familiar environment. It governs the motion of moons around planets, planets around stars, stars around galactic centers, and galaxies within local groups. Human life unfolds entirely inside regions where gravity remains the strongest large-scale influence. Nothing in ordinary experience prepares us for the astonishing realization that beyond these local neighborhoods, across the vast emptiness, separating distant galaxy clusters, gravity appears to be losing a quiet contest against something far more mysterious. The remarkable story of dark energy begins precisely where gravity seems least likely to surrender. For billions of years, gravity patiently shaped the universe into the magnificent cosmic landscape visible today. Yet as astronomers looked farther into space and deeper into time, they began finding evidence that this ancient force, so dependable and so familiar, was no longer fully in control of the universe's largest destiny. For much of the 20th century, astronomers agreed on one simple expectation. The universe was expanding, but the expansion should be slowing down. The only real question was how quickly that slowing was taking place. Some believed gravity would eventually stop the expansion entirely. Others thought the expansion would continue forever, becoming slower with each passing billion years. Whatever the future held, almost everyone assumed gravity was gradually applying the brakes. The challenge was finding a way to measure that slowing directly. Looking at the universe is unlike observing a laboratory experiment. No one can watch galaxies for billions of years to see how their speeds change. Human lives are far too short. Instead, astronomers needed another method, one that would allow them to compare different moments in the history of the universe without waiting for unimaginable lengths of time to pass. Fortunately, the universe provides a remarkable advantage. Light does not travel instantly. Every beam of light requires time to cross space. When looking at the moon, we see it as it appeared about 1 second ago. Looking at the sun reveals it as it was roughly 8 minutes earlier. A nearby star appears as it was several years in the past. The most distant galaxies reveal themselves as they existed billions of years ago, long before Earth had taken its present form. In a sense, every telescope is also a time machine. The farther into space it observes, the farther into the past it looks. Astronomers realized that by studying galaxies at different distances, they could compare different chapters of cosmic history. Nearby galaxies represented the relatively recent universe. Extremely distant galaxies revealed an era when the universe was much younger. This idea opened an extraordinary opportunity. If the expansion had truly been slowing under gravity, then the ancient universe should show evidence of a different expansion rate than the modern universe. The challenge became finding objects so bright and reliable that their distances could be measured across billions of light years. Among the most valuable objects for this purpose are exploding stars known as type Ia supernovae. These events occur under very specific conditions, producing explosions with nearly the same intrinsic brightness. Because their true brightness is fairly consistent, astronomers can compare how bright they appear from Earth to estimate how far away they are. A dimmer explosion is generally farther away, while a brighter one is closer. These spectacular events became known as standard candles, not because they resemble ordinary candles, but because they provide dependable reference points across enormous distances. Imagine walking through a long avenue lined with identical street lamps. Even without knowing the exact distance to each lamp, you could estimate which ones are farther simply by how small and faint they appear. Astronomers apply a similar principle when observing these distant stellar explosions. The universe itself provides the lights, while careful measurements reveal the scale of cosmic distances. During the 1990s, several international teams devoted years to searching for these rare explosions. Powerful telescopes repeatedly photographed distant regions of the sky, looking for tiny points of light that suddenly appeared where nothing had been visible before. Discovering even a single suitable supernova required patience, careful observation, and repeated confirmation. Thousands of images were examined, compared, and analyzed with extraordinary precision. As more observations accumulated, researchers began calculating the expansion history of the universe. The expectation remained straightforward. The measurements should reveal that expansion had gradually slowed over billions of years. Instead, something deeply unexpected emerged from the data. The distant supernovae appeared slightly dimmer than predicted. At first glance, the difference seemed almost insignificant. It was small enough that many researchers questioned whether the measurements contained hidden errors. Perhaps dust between galaxies was absorbing more light than expected. Perhaps the exploding stars themselves differed slightly from one another. Perhaps an unnoticed problem existed in the instruments or calculations. Every possibility had to be examined carefully. Scientific discoveries are rarely accepted after a single surprising observation. Extraordinary claims require extraordinary evidence. The research teams spent months checking every assumption, comparing independent observations, refining their calculations, and searching for mistakes that might explain the unexpected results. The more carefully the data were examined, the more stubborn the conclusion became. The observations continued pointing toward the same astonishing picture. Billions of years ago, the expansion of the universe had indeed been slower than it is today. Instead of gradually losing speed, the expansion had begun increasing. Somewhere during cosmic history, the universe had quietly shifted into a new behavior. This result surprised even the scientists who discovered it. Many later described their own disbelief. During those first analyses, they had set out expecting to measure how gravity slowed the universe. Instead, they found evidence that something was causing space itself to expand more rapidly over time. It was not a dramatic acceleration like a racing automobile, suddenly speeding down a highway. On human scales, the effect is extraordinarily gentle. Even over millions of years, The difference would be impossible to notice without precise astronomical measurements. Yet across billions of years, and across distances involving countless galaxies, that tiny acceleration completely changes the long-term evolution of the cosmos. Imagine placing two floating leaves on the surface of a calm river. At first, they drift apart slowly. As time passes, instead of separating more gently, the distance between them begins increasing faster and faster, even though neither leaf is actively moving under its own power. The river itself is quietly stretching beneath them. While no river behaves this way, the analogy captures something of the strange behavior astronomers discovered in the universe. The implications were enormous. If gravity alone governed cosmic expansion, such acceleration should not occur. Some additional influence appeared to be working on scales larger than galaxies and galaxy clusters. Whatever this influence was, it acted in the opposite direction from gravity, encouraging the expansion rather than resisting it. Scientists eventually gave this mysterious influence a simple name: dark energy. The name did not explain its nature. It merely acknowledged that something unknown seemed responsible for the accelerating universe. In science, names often arrive long before understanding. Giving a phenomenon a name allows researchers to discuss it clearly, while continuing the search for its true identity. As more observations were collected over the following years, confidence in the discovery steadily grew. Independent methods of measuring the universe supported the same conclusion. Studies of ancient light left over from the early universe, detailed maps of galaxy distributions, and increasingly precise measurements all pointed toward the same remarkable picture. The acceleration was not an illusion. It appeared to be a genuine feature of the universe itself. Today, this quiet acceleration is considered one of the defining characteristics of the modern cosmos. Every immense region between distant galaxies is slowly growing larger. Every billion years, the universe becomes more spacious than before. The process unfolds with extraordinary patience, almost impossible to notice within a human lifetime, yet relentless across cosmic time. It is a silent transformation, unfolding everywhere at once, guided by a phenomenon that remains one of the deepest mysteries ever encountered. One of the first things to understand about dark energy is that, despite its name, no one has ever seen it. There is no telescope that can photograph it, no camera that can capture its shape, and no spacecraft that has traveled through a cloud of dark energy and reported what it found. Unlike stars, planets, or galaxies, dark energy does not produce light. It does not glow in the darkness of space, and it does not cast shadows. It remains completely invisible to every instrument that observes the universe in ordinary ways. The name itself can be slightly misleading. The word dark often brings to mind something black, hidden, or mysterious in appearance. In astronomy, however, dark usually means something much simpler. It refers to anything that cannot be detected directly through light. Dark matter earned its name for this reason, and dark energy follows the same tradition. The name does not describe what it looks like. It simply reflects how little is currently known about its true nature. This is an important distinction because dark energy and dark matter are entirely different ideas. Their names sound similar, but their behavior could hardly be more different. Dark matter appears to act like an invisible form of mass. It pulls galaxies together through gravity, helping them maintain their structure and influencing how they move. Dark energy, on the other hand, appears to have the opposite large-scale effect. Instead of drawing galaxies closer, it seems to encourage the expansion of space, allowing distant galaxies to drift farther apart as the universe grows older. It is easy to imagine that dark energy might be some kind of invisible gas filling the universe, gently blowing galaxies away from one another. This image is understandable, but it does not match what astronomers observe. A gas moves from one place to another. It can form clouds, become denser in certain regions, or be pushed by other forces. Dark energy does not appear to behave this way. As far as observations can tell, it seems to exist almost uniformly throughout the observable universe. This remarkable uniformity is one of its most puzzling features. The universe is full of enormous differences. Some regions contain crowded clusters of galaxies with trillions of stars. Other regions are vast cosmic voids where galaxies are separated by immense distances. Yet dark energy does not seem to gather around galaxies or avoid empty space. Instead, it appears to remain almost evenly distributed everywhere, quietly present, regardless of what surrounds it. Imagine standing inside a vast fog that is perfectly uniform. No matter which direction you walk, the fog never becomes thicker or thinner. There are no visible edges, no swirling clouds, and no empty patches. Every step carries you through the same gentle mist. This analogy is far from perfect, because dark energy cannot actually be seen or felt like fog, but it hints at the extraordinary smoothness that astronomers believe dark energy possesses across the cosmos. Another common misunderstanding is the idea that dark energy pushes galaxies through space like wind pushing leaves across the ground. The observation suggests something subtler. Galaxies are not being blown away from one another by a force traveling through space. Instead, the space between them appears to be increasing. It is the expansion of the universe itself that grows stronger over time, carrying distant galaxies farther apart without requiring them to travel through space in the ordinary sense. This difference becomes easier to appreciate when considering our own surroundings. Dark energy is believed to exist here as well. It is present within our galaxy, within our solar system, and even in the space surrounding Earth. Yet it does not tear planets from their orbits or pull apart the stars of the Milky Way. The reason is that its influence is extraordinarily weak on small scales. Gravity easily dominates within galaxies, solar systems, and planetary systems, keeping familiar structures intact. Only when distances become unimaginably large does dark energy begin to reveal itself. Between enormous groups of galaxies, where gravity becomes comparatively weak across millions of light years, the cumulative effect of dark energy gradually becomes significant. It is not because dark energy suddenly grows stronger. Rather, gravity becomes less effective over these immense separations, allowing the quiet influence of dark energy to shape the expansion of the universe. Scientists often describe dark energy as accounting for roughly 70% of the total energy content of the universe. At first, this statement sounds astonishing. How can something that dominates the cosmos remain almost completely unknown? The answer lies in the fact that abundance does not always make something easy to study. Air surrounds us constantly, yet many of its microscopic properties remained mysterious until modern science developed the necessary tools. Dark energy may be vastly more abundant than ordinary matter, but its interactions with the universe appear so subtle that detecting them requires observations spanning billions of light years. Even the word energy can create confusion. In daily life, energy usually refers to electricity flowing through wires, sunlight warming the ground, or fuel powering an engine. Dark energy does not resemble any of these familiar forms. It does not appear to be a source of usable power, nor does it behave like heat or radiation. The term was chosen because it fits naturally within the language of physics, but it should not be imagined as an invisible fuel spread across the cosmos. Perhaps the most honest description is also the simplest. Dark energy is a name for the unknown cause of the universe's accelerating expansion. It is not a complete explanation. It is a label attached to a phenomenon whose true identity remains hidden. Scientists know something is influencing the largest scales of the universe because the observations consistently point in the same direction. Beyond that, many possibilities remain open. Some researchers suspect dark energy has existed since the earliest moments of cosmic history, remaining nearly unchanged for billions of years. Others wonder whether it might slowly evolve over time, becoming stronger or weaker as the universe ages. There are even ideas suggesting that dark energy may not be a substance at all, but rather a sign that our understanding of gravity is incomplete. Each possibility offers a different picture of the cosmos, and each is being carefully explored through observation and theory. One of the most peaceful aspects of this mystery is its patience. Dark energy does not announce itself through dramatic explosions or sudden transformations. It works quietly, almost invisibly, across distances so immense that human imagination struggles to contain them. Every second that passes, the universe becomes slightly larger than it was before. Every million years, galaxies drift a little farther apart. Every billion years, the cosmic landscape changes almost imperceptibly, guided by an influence that remains hidden behind one of the greatest unanswered questions in all of astronomy. Measuring the expansion of the universe is one of the most delicate tasks in astronomy. Unlike measuring the length of a table or the height of a mountain, there is no giant ruler stretching across space. Astronomers cannot travel to distant galaxies, place instruments beside them, and record their positions directly. Every piece of information must arrive as light, sometimes after traveling for billions of years, before finally reaching a telescope on Earth. This means that almost everything known about the universe depends on interpreting light correctly. Every tiny beam carries a story. Hidden within its brightness, color, and direction are clues about where it originated, how far it has traveled, and how the universe has changed during its journey. The challenge is learning how to read those clues with enough precision that reliable conclusions can be drawn from them. Distance is the foundation of every measurement. Before asking how fast a galaxy is moving away, astronomers must first know approximately how far away it is. This may sound simple, but measuring cosmic distances has occupied generations of scientists. The universe offers no convenient signs saying 1 million light-years or 5 billion light-years. Instead, researchers have gradually built what is often called the cosmic distance ladder, a series of methods that overlap and support one another. The nearest distances can be measured using geometry. As Earth travels around the Sun, nearby stars appear to shift ever so slightly against the much more distant background stars. This tiny apparent movement is called parallax. It is similar to holding a finger in front of your face and looking at it first with one eye, then the other. Your finger seems to move, while distant objects remain almost fixed. The amount of that apparent movement reveals the distance. Parallax works beautifully for relatively nearby stars, but eventually the distances become so great that the shift is too small to measure accurately. Astronomers must then rely on brighter objects that can be seen much farther away. Certain types of stars brighten and dim in regular patterns. By studying these repeating changes, scientists discovered that the true brightness of these stars can be estimated. Comparing their true brightness with how bright they appear from Earth allows their distances to be calculated. Each method extends the reach of the previous one. Nearby stars help measure slightly more distant stars. Those stars help measure nearby galaxies. Nearby galaxies become reference points for galaxies even farther away. Like carefully constructing a ladder one step at a time, each level depends upon the stability of the one below it. Decades of observations have refined this system until it reaches astonishing distances across the observable universe. Once distance is known, astronomers compare it with redshift. As discussed earlier, redshift measures how much the light from a galaxy has been stretched during its journey. Larger redshifts generally indicate greater expansion between the galaxy and Earth. By combining these two pieces of information, distance and redshift, scientists can build a detailed picture of how the universe has expanded throughout cosmic history. The relationship is not perfectly simple. Nearby galaxies possess their own individual motions, in addition to the overall expansion of space. Some galaxies drift toward one another because gravity pulls them together. Others orbit within galaxy clusters. These local motions create small differences that astronomers must carefully account for before studying the much larger pattern of cosmic expansion. Imagine watching leaves floating along a wide river. Each leaf follows the current, but small breezes and gentle ripples also influence their paths. If the goal is to measure the speed of the river itself, those smaller motions must be understood and averaged out. In much the same way, astronomers study enormous numbers of galaxies to reveal the overall expansion hidden beneath countless local movements. Modern telescopes have transformed this work. Sensitive digital detectors collect faint light that would have been impossible to observe only a few decades ago. Some galaxies appear so dim that their light began its journey long before the Earth existed. Capturing these ancient photons often requires many hours of observation, with telescopes remaining perfectly steady while collecting the smallest traces of light from the depths of space. Every observation must also overcome Earth's atmosphere. Although our atmosphere protects life, it gently blurs incoming starlight. This is why stars appear to twinkle. The same turbulence that creates beautiful sparkling skies also reduces the sharpness of astronomical images. Observatories are therefore built on high mountains where the air is thinner and steadier. Space telescopes go even farther by operating completely above the atmosphere, providing remarkably clear views of the distant universe. The expansion of the universe is measured not through a single observation, but through the combined efforts of thousands of astronomers working over many decades. One telescope measures the brightness of distant galaxies. Another studies their spectra. Others map the distribution of galaxies across enormous regions of space. Still others examine the faint glow left behind from the early universe. Each observation contributes another piece to an immense cosmic puzzle. Interestingly, different methods of measuring the universe do not always produce exactly the same results. In recent years, astronomers have noticed a small but persistent disagreement between some measurements of the current expansion rate. This difference has become known as the Hubble tension. It does not necessarily mean that any observation is incorrect. Instead, it may suggest that there are still aspects of the universe that remain hidden from present understanding. Some researchers believe improved measurements will eventually resolve the disagreement through greater precision. Others wonder whether the tension hints at entirely new physics waiting to be discovered. History shows that small inconsistencies have sometimes led to major scientific breakthroughs. A tiny mismatch in observations can occasionally reveal an entirely new layer of reality that had previously gone unnoticed. Despite these remaining questions, one conclusion has become remarkably secure. Independent techniques, developed by different groups using different kinds of observations, all point toward the same broad picture. The universe is expanding, and that expansion has been accelerating for billions of years. Whether astronomers observe exploding stars, ancient background light, or the large-scale arrangement of galaxies, they continue finding evidence that supports this extraordinary conclusion. There is something quietly comforting about the patience required for these measurements. Every answer arrives one observation at a time, collected across decades by people separated by continents, languages, and generations. No single telescope reveals the entire story. Instead, humanity gradually pieces together the history of the cosmos from countless fragments of ancient light, each photon carrying a tiny whisper from the distant past. Through this slow and careful process, the expanding universe becomes not just an idea, but a measurable reality, revealing itself with remarkable consistency across the vast silence of space. At first glance, the universe appears to be filled with isolated islands of light. A telescope points toward the night sky and reveals one galaxy here, another there, each surrounded by enormous stretches of darkness. It is easy to imagine that these galaxies are scattered randomly, like grains of sand tossed across a beach. The true structure of the universe, however, is far more organized. On the largest scales, galaxies form an immense network that stretches across billions of light years, creating one of the most beautiful patterns ever discovered. A single galaxy is already an astonishing object. The Milky Way, the galaxy that contains our solar system, is thought to hold hundreds of billions of stars. Around many of those stars orbit planets, while between them drift vast clouds of gas and microscopic dust. Hidden near the center is a supermassive black hole whose mass is millions of times greater than that of our Sun. Yet despite its enormous size, the Milky Way is only one member of a much larger cosmic family. Galaxies rarely exist entirely alone. Gravity slowly gathers them into groups that remain bound together for billions of years. Our own galaxy belongs to a relatively small collection known as the local group. Alongside the Milky Way are dozens of smaller galaxies and the large spiral galaxy Andromeda. These galaxies are connected by gravity, moving through space in a slow cosmic dance that unfolds over unimaginable spans of time. Far beyond the local group lie even larger collections called galaxy clusters. A single cluster may contain hundreds or even thousands of galaxies. These enormous systems are among the largest gravitationally bound structures in the universe. Their combined mass is so great that they influence the motion of everything within them. Individual galaxies travel around the cluster, much as planets orbit a star. Although their journeys require hundreds of millions or even billions of years to complete, the spaces inside galaxy clusters are not empty. Between the galaxies lies extremely hot gas reaching temperatures of millions of degrees. This gas is so thin that it would appear almost like a perfect vacuum by everyday standards. Yet across such enormous volumes, it contains tremendous amounts of matter. Even more remarkable, most of the cluster's total mass does not come from the visible galaxies or the glowing gas. It appears to come from invisible dark matter, whose gravity quietly holds the entire structure together. When astronomers began mapping larger and larger regions of the universe, they expected to find clusters scattered more or less evenly through space. Instead, an extraordinary pattern emerged. Clusters themselves gathered into even larger arrangements. Long chains of galaxies stretched across the cosmos like delicate threads, connecting massive concentrations while leaving vast empty regions between them. This pattern became known as the cosmic web. The name is wonderfully descriptive. If the universe could somehow be viewed from unimaginably far away, the distribution of galaxies would resemble an intricate three-dimensional network. Bright filaments extend across hundreds of millions of light years. At the points where several filaments meet, enormous galaxy clusters gather. Between these filaments lie gigantic cosmic voids, regions where very few galaxies exist at all. The cosmic web is difficult to picture because nothing like it exists in everyday life. One useful comparison is a network of rivers viewed from high above. Rivers branch into smaller streams, which eventually reconnect elsewhere, creating an interconnected landscape. The cosmic web behaves in a somewhat similar manner, except that its strands are made of galaxies instead of flowing water, and its scale exceeds anything found on Earth. Another helpful image is the delicate pattern formed by frost spreading across a cold window. Thin branches grow outward, divide repeatedly, and create elegant structures that seem almost alive. Although the physical processes are entirely different, the visual appearance captures something of the graceful complexity found in maps of the large-scale universe. Remarkably, these enormous structures did not exist immediately after the universe began. In its earliest stages, matter was distributed much more evenly. Tiny differences in density, almost unimaginably small, gradually became amplified through gravity. Regions containing slightly more matter attracted even more material over billions of years. Slowly, almost imperceptibly, the first filaments emerged. Galaxy clusters formed where several growing filaments intersected, while neighboring regions became emptier as matter flowed away toward the denser areas. This process required extraordinary patience. The universe did not construct its largest structures quickly. Gravity worked continuously, never hurrying, never resting. Over billions of years, countless individual motions combined into the magnificent architecture visible today. Every galaxy, every cluster, and every filament became part of an immense interconnected design stretching across the observable universe. Dark energy entered this story surprisingly late. For much of cosmic history, gravity dominated the formation of large structures. Galaxies merged, clusters grew, and the cosmic web became increasingly pronounced. The universe was like a vast city still under construction, with gravity steadily adding new buildings, roads, and neighborhoods. Then, as the universe expanded and matter became more spread out, another influence gradually began asserting itself. Because dark energy appears to act throughout space itself, its effect becomes increasingly important as galaxies move farther apart. While gravity grows weaker with increasing distance, dark energy seems remarkably persistent over immense scales. The gentle expansion it encourages slowly begins to overcome gravity's ability to pull distant structures together. This does not mean that galaxy clusters suddenly fall apart. Structures already held together by gravity remain stable. The Milky Way will not drift away from its neighboring stars because of dark energy. The local group will not quietly dissolve tomorrow. Gravity is still overwhelmingly stronger within these bound systems. Instead, dark energy changes the future growth of the cosmic web. Regions that have not yet become gravitationally bound find it increasingly difficult to collapse into new structures. Galaxy clusters separated by enormous distances slowly drift farther apart. The great filaments connecting the universe continue to stretch as the expanding fabric of space quietly increases the distances between them. If someone could observe the universe over tens of billions of years, the change would appear almost poetic. The magnificent web would slowly become more delicate. Clusters would grow increasingly isolated. The immense voids between them would widen, becoming larger than they are today. The universe would remain beautiful, but its beauty would become quieter, calmer, and lonelier as the great structures gradually separated from one another. The cosmic web reminds us that the universe is not simply a collection of isolated objects scattered through emptiness. Everything belongs to a much larger pattern, one shaped first by gravity and increasingly influenced by dark energy. Across billions of light years, galaxies participate in a slow and graceful evolution that no single lifetime could ever witness directly. Yet through careful observation, humanity has learned to recognize this vast architecture, revealing a universe whose largest structures are as elegant as they are immense, suspended within an ever-expanding sea of space. When most people imagine empty space, they picture absolute nothingness. A perfect vacuum seems like the complete absence of everything. No stars, no planets, no light, no sound, no air. Just endless darkness stretching in every direction. It feels natural to think that once every object has been removed, nothing remains. Modern astronomy paints a far more fascinating picture. Even the emptiest regions of the universe are not truly empty. They may contain only a few atoms scattered across enormous distances, but there is something even more fundamental present. Space itself exists. It is not simply a backdrop on which the universe unfolds. It possesses properties of its own, and understanding those properties has become one of the most important steps toward understanding dark energy. On Earth, it is almost impossible to create a perfect vacuum. Even inside the most advanced laboratory chambers, tiny numbers of atoms remain. Molecules cling to the chamber walls, stray particles drift through the container, and radiation from the surrounding environment quietly enters. Scientists can remove almost everything, but reaching complete nothingness proves remarkably difficult. Outer space is vastly emptier than any laboratory. Between galaxies lie regions so immense that a single atom may be separated from the next by several meters, or even farther. Compare the air around us. These regions are unimaginably sparse, yet they are still not completely empty. More importantly, physics suggests that even if every atom, every photon of light, and every particle of dust could somehow be removed, something would still remain. The space itself would still exist. This idea feels unusual because everyday experience encourages us to think of space as nothing more than distance. A room seems empty after the furniture is removed, but the room itself remains. Likewise, if every galaxy vanished from the universe, the vast framework in which those galaxies once existed would still be present. For centuries, scientists debated whether empty space was truly nothing, or whether it possessed its own physical reality. This question became especially important after the development of modern physics during the 20th century. One of the greatest discoveries was that empty space is surprisingly active on incredibly tiny scales. Although it appears calm from our perspective, the microscopic world behaves very differently. According to quantum physics, the smallest scales of nature are never completely still. Instead, they exhibit continuous tiny fluctuations that occur everywhere, even within regions that appear perfectly empty. Imagine standing beside a calm lake just before sunrise. From a distance, the water looks perfectly smooth. As you move closer, however, you begin noticing countless tiny ripples spreading across its surface. None of them are dramatic. Most disappear almost immediately. Yet, the surface is never truly motionless. Physicists believe something similar happens within empty space itself. This does not mean invisible waves are constantly crashing through the universe like ocean tides. The comparison simply captures the idea that absolute stillness may not exist on the smallest possible scales. What appears completely empty, from a human perspective, may possess an incredibly subtle level of activity beyond ordinary observation. These tiny quantum fluctuations are extraordinarily difficult to imagine because they occur at scales vastly smaller than atoms. They cannot be seen directly with microscopes, nor can they be experienced in daily life. Their existence is inferred through mathematical descriptions and carefully designed experiments that reveal their indirect effects. If empty space possesses even a tiny amount of energy everywhere, an astonishing possibility emerges. The universe contains an enormous amount of space. Far more space exists than matter. Galaxies occupy only a tiny fraction of the observable universe. Most of the cosmos consists of enormous regions separating galaxies, galaxy clusters, and the delicate filaments of the cosmic web. If every cubic centimeter of that vast emptiness contained even the smallest amount of energy, the combined total across the observable universe could become enormous. This simple observation has fascinated physicists for decades. Could dark energy simply be the energy of empty space itself? The idea sounds elegant because it naturally explains why dark energy appears almost perfectly uniform. Empty space exists everywhere. Unlike galaxies, which gather into clusters, or stars, which form inside galaxies, space fills the entire universe evenly. If space itself possesses energy, that energy would also appear everywhere. This possibility also fits another important observation. Dark energy does not seem interested in where galaxies happen to be located. Whether astronomers observe dense galaxy clusters or enormous cosmic voids, the large-scale expansion behaves remarkably consistently. It is as though the expansion depends not on where matter exists, but on the properties of space itself. This concept represents a profound change in perspective. For much of history, empty space was treated as little more than a stage upon which the universe performed. Matter and energy were considered the true actors, while space merely provided the setting. Modern physics suggests the stage may itself participate in the story. Space can stretch. Space can curve. Space can carry light. And perhaps space also possesses its own energy. None of these ideas come naturally to human intuition, because our senses evolved to understand forests, rivers, mountains, and eyes. not billions of light years of expanding cosmic geometry. Yet every generation of astronomers has discovered that the universe often behaves in ways far stranger than everyday experience would ever suggest. Interestingly, even if dark energy does arise from the energy of empty space, enormous questions remain unanswered. Why does space contain exactly this amount of energy and not much more? Why has this energy become important only during the later history of the universe? Why does it appear so remarkably uniform across unimaginably large distances? These questions remain among the deepest mysteries in modern cosmology. Scientists have developed sophisticated mathematical models, but no explanation has yet gained universal acceptance. Some calculations predict values enormously larger than what astronomers actually observe, making the puzzle even more intriguing. Despite these uncertainties, the idea itself carries a certain quiet beauty. The emptiest places in existence may not be empty at all. The vast darkness between galaxies, which once seemed like meaningless gaps, may actually hold one of the universe's greatest secrets. Every immense cosmic void, every silent stretch separating distant galaxy clusters, and every region where almost nothing appears to exist could be gently participating in the expansion of the cosmos. When looking into the night sky, it is easy to focus on the stars. Their light naturally attracts our attention. Yet, the overwhelming majority of the universe is not made of stars. It is made of the immense spaces between them. Those silent regions, once thought to be little more than emptiness, may ultimately prove to be the key to understanding why the universe continues expanding ever faster, patiently, and quietly. Across the endless depths of cosmic time, the idea that empty space might contain energy sounds almost like a contradiction. In everyday life, energy usually belongs to something we can identify. A glowing light bulb uses electrical energy. A moving train possesses kinetic energy. A warm fireplace gives off heat. Every familiar form of energy seems connected to an object or a process that can be seen and understood. Empty space appears to offer neither. It seems to contain nothing at all. Yet, modern physics suggests that this intuition is incomplete. To understand why, it helps to think about the smallest scales of nature. The world we experience every day feels solid and predictable. A book rests on a table. A mountain remains where it has stood for thousands of years. The moon follows its orbit with remarkable consistency. On these familiar scales, the universe appears calm and orderly. As scientists began exploring matter at smaller and smaller scales, however, they discovered a world that behaves very differently. At the level of atoms and the particles inside them, certainty gives way to probability. Instead of following perfectly predictable paths, tiny particles behave in ways that can only be described through likelihoods and possibilities. This strange microscopic world is the domain of quantum physics. Quantum physics has earned a reputation for being mysterious, but many of its central ideas arise from careful observation rather than imagination. Again and again, experiments have shown that nature behaves differently on extremely small scales than human intuition would suggest. The mathematics describing these behaviors has become one of the most successful scientific frameworks ever developed, accurately predicting countless observations over many decades. One surprising consequence of this theory is that complete stillness may not exist. Imagine placing a perfectly polished marble into the deepest bowl imaginable. Common sense suggests that eventually the marble would come to rest at the very bottom, completely motionless. Quantum physics tells a different story. On the smallest scales, absolute rest becomes impossible. There is always a tiny amount of unavoidable activity built into the fabric of reality itself. This does not mean objects constantly bounce around in obvious ways. Rather, the microscopic universe seems to possess an irreducible level of motion that cannot simply disappear, even when every possible source of ordinary energy has been removed. A faint background of quantum activity appears to remain. Physicists sometimes describe this underlying activity as vacuum energy. The word vacuum refers to empty space, while energy reflects the idea that even this apparent emptiness may possess physical properties. The vacuum is therefore not imagined as a lifeless void, but as something with subtle characteristics of its own. One helpful analogy is a quiet forest at night. From a distance, everything appears perfectly still. The trees do not seem to move. The air feels calm. The darkness suggests complete silence. Yet if someone listens carefully enough, faint sounds begin to emerge. Leaves gently shift. Tiny insects move through the undergrowth. A distant breeze brushes against the branches. What first appeared completely motionless reveals itself as quietly active. The comparison is imperfect, because quantum activity is nothing like insects or moving leaves. But it captures the important idea that apparent stillness does not necessarily mean complete inactivity. Another analogy comes from the surface of the ocean. On certain mornings, the sea appears almost perfectly flat when viewed from high above. Yet anyone floating upon it soon notices countless tiny ripples rising and fading continuously. No single ripple dominates the surface. Instead, endless small motions combine into a gentle background pattern that never completely disappears. According to quantum theory, something similarly subtle may exist within space itself. This possibility becomes especially fascinating when combined with the enormous scale of the universe. The observable universe is almost unimaginably vast. Galaxies occupy only a tiny fraction of its total volume. Most of existence consists of immense regions where very little ordinary matter can be found. If every part of that enormous volume possesses even the smallest amount of vacuum energy, the combined total could become significant enough to influence the expansion of the universe. This is one of the reasons vacuum energy has become one of the leading ideas in the search to understand dark energy. The concept offers an elegant explanation for why dark energy appears everywhere. Since empty space exists throughout the universe, its energy would naturally be present everywhere as well. There would be no need for invisible clouds or hidden particles spreading unevenly across space. The energy would simply belong to space itself. Yet, elegance alone is not enough. Science depends on agreement between theory and observation, and here an extraordinary problem appears. When physicists use quantum theory to estimate the amount of vacuum energy that empty space should contain, the answer becomes astonishingly large. In fact, the predicted value is so enormous that it exceeds the amount suggested by astronomical observations by an almost unimaginable margin. This disagreement is often described as one of the greatest mismatches in all of physics. The universe does appear to contain something behaving like vacuum energy, but not nearly as much as many straightforward calculations predict. Somewhere within our understanding, an important piece of the puzzle seems to be missing. Imagine weighing a single feather and expecting it to equal the mass of an entire mountain. The difference would immediately suggest that something fundamental had gone wrong in the calculation. The disagreement between theoretical estimates of vacuum energy and the value implied by observations is vastly greater than even that comparison suggests. For decades, scientists have searched for explanations. Perhaps the calculations are incomplete. Perhaps different contributions to vacuum energy almost perfectly cancel one another. Perhaps dark energy has an entirely different origin. Or perhaps our current understanding of quantum physics and gravity has not yet reached the level needed to describe the universe correctly. Each possibility remains an active area of research. What makes this mystery especially remarkable is that it does not arise because observations are absent. Astronomers have collected increasingly precise measurements of the expanding universe, while physicists have developed extraordinarily successful quantum theories describing microscopic particles. Both fields work remarkably well on their own. The challenge comes when trying to combine them into a single picture that explains dark energy naturally. In many ways, dark energy stands at the meeting point of the two largest frontiers in modern physics: One frontier explores the smallest structures imaginable, the quantum world of particles and microscopic fluctuations. The other explores the largest structures imaginable, the expanding universe of galaxies, clusters, and cosmic horizons. Somehow these two extremes may be connected. Perhaps the quiet activity of empty space on unimaginably tiny scales ultimately shapes the destiny of the entire observable universe. If so, the smallest features of reality would influence the largest structures in existence, linking the microscopic and the cosmic in a way that is both unexpected and profoundly beautiful. Every night, countless regions of apparently empty space stretch silently between the galaxies. They appear dark and uneventful, yet they may contain one of the deepest secrets in nature. Within those vast expanses where almost nothing can be seen, the answer to why the universe continues its gentle, accelerating expansion may have been present all along, hidden not inside the stars, but within the quiet fabric of space itself. The story of dark energy is closely connected to one of the most famous figures in science, Albert Einstein. Long before the discovery of cosmic acceleration, Einstein was already trying to understand how the universe itself behaves on the largest possible scales. His theory of general relativity, published in 1915, completely changed how scientists think about gravity. Before this theory, gravity was imagined as a force acting between objects, similar to an invisible pull stretching across space. Einstein introduced a different picture. In his view, gravity is not simply a force, but a consequence of the shape of space and time itself. Massive objects like stars and planets bend the fabric of space-time, and this curvature determines how other objects move. In this framework, planets orbit stars not because they are pulled by an invisible rope, but because they are following the natural curves of space-time. This idea may sound abstract, but it matches reality with extraordinary accuracy. General relativity explains the orbit of planets, the bending of light near massive objects, and even the existence of black holes. It became one of the most successful scientific theories ever created. However, when Einstein first applied his equations to the entire universe, something unexpected happened. The equations suggested that the universe could not remain static. According to the mathematics, a universe filled with matter should either expand or contract. At the time, most scientists believed the universe was eternal and unchanging on large scales, so this result felt uncomfortable. To resolve this, Einstein introduced an additional term into his equations. This term acted like a kind of hidden energy built into space itself. It was designed to counteract gravity on cosmic scales, allowing the universe to remain stable and unchanging. He called this addition the cosmological constant. The idea was simple in appearance, but deep in meaning. If space itself contained a form of energy, it could produce a repulsive effect that balances the attractive pull of gravity. In Einstein's original vision, this constant was not meant to explain an expanding universe. It was introduced specifically to prevent expansion or contraction altogether, keeping the cosmos in a steady state. For a short time, the cosmological constant served its purpose as a mathematical adjustment. But soon after, observational astronomy began to change everything. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us. This meant the universe is not static at all. It is expanding. Once this discovery became clear, Einstein reportedly considered the cosmological constant unnecessary. According to popular accounts, he later referred to it as his greatest mistake. Although historians debate the exact wording and context, what is certain is that the idea was largely set aside for many decades, becoming a quiet footnote in the history of cosmology. For much of the 20th century, the cosmological constant was treated as an abandoned concept. The expanding universe was explained without it, and gravity was thought to be the dominant influence on cosmic evolution. The idea of a built-in energy of space remained mathematically possible, but physically unimportant in most models. Then, At the end of the century, the situation changed dramatically. When astronomers discovered that the expansion of the universe is accelerating, they needed a new explanation. Gravity alone could not produce this behavior. Something was acting in the opposite direction, gently increasing the rate at which space itself expands. Suddenly, the old idea of a cosmological constant returned in a completely new form. If space contains a constant energy everywhere, it would produce a uniform effect across the entire universe. It would not cluster around galaxies or form structures. Instead, it would influence the expansion of space itself, causing it to grow faster over time. This description matches the behavior of dark energy remarkably well. Because of this, many modern cosmological models describe dark energy using a form of Einstein's cosmological constant. In this interpretation, dark energy is not something that changes or moves. It is simply a fixed property of space itself, present everywhere and at all times, gently shaping the expansion of the universe. However, this is not the final answer. Even though the cosmological constant model fits many observations, it raises deep questions. Why does this constant have the value it does? Why is it so small compared to theoretical predictions from quantum physics? And why did it become significant only in the later stages of cosmic history, rather than dominating from the beginning? These questions remain open. Some scientists prefer the cosmological constant because of its simplicity. It adds very little complexity to existing equations and matches current data quite well. Others believe dark energy might be more dynamic, possibly changing over time or interacting with other unknown aspects of physics. In those models, the cosmological constant is only an approximation of something deeper. What makes this story especially interesting is how ideas can disappear and then return in new forms. The cosmological constant was once introduced to force the universe into a static state. Later, it was abandoned when expansion was discovered. Now it has returned as one of the leading explanations for cosmic acceleration. The same mathematical idea has shifted meaning as our understanding of the universe has evolved. This pattern reflects something important about science itself. Concepts are not always right or wrong in a simple sense. Sometimes they are ahead of their time, waiting for new evidence or new contexts to reveal their relevance again. Today, Einstein's equations still form the foundation of modern cosmology. When astronomers model the expansion of the universe, they often include a term very similar to the cosmological constant. It acts as a simple representation of dark energy, capturing its large-scale effects even if its true nature remains unknown. In a quiet sense, this means that the structure of the expanding universe is still being described using an idea that began over a century ago. A term introduced to preserve a static cosmos now helps describe a cosmos that is expanding faster and faster. As scientists continue to study distant galaxies, ancient light, and the subtle geometry of space-time, Einstein's equations remain at the center of the investigation. They describe how matter curves space, how energy influences expansion, and how the universe evolves over time. Yet within those equations, one small term continues to represent one of the greatest mysteries in existence. A simple constant that may be written in a line of mathematics appears to govern the fate of everything, from the largest galaxy clusters to the vast emptiness between them. The universe today can be described with remarkable precision, yet at the same time it feels strangely incomplete. Astronomers can measure how fast it expands, map the distribution of galaxies across billions of light years, and calculate how much matter exists in different forms. Physicists can describe the behavior of particles with extraordinary accuracy, predicting outcomes of experiments that take place deep underground or inside powerful accelerators. Despite all this knowledge, one major ingredient of the cosmos still resists full explanation. Dark energy remains known only through its effects, not through its true nature. This creates a peculiar situation. On one hand, the behavior of the universe is well measured. On the other hand, the cause of that behavior is not understood. It is as if someone could precisely track how a river flows, how fast it moves, and how its currents change over time, but had no explanation for what drives the water itself. The success of modern cosmology is built on a combination of observation and theory. Observations tell us what the universe is doing. Theory attempts to explain why. When both align, understanding deepens. When they do not, mystery emerges. Dark energy sits precisely at this boundary between knowledge and uncertainty. One of the most striking features of dark energy is how smoothly it appears to be distributed. Galaxies cluster together, stars form in dense regions, and matter gathers into complex structures. Dark energy does not seem to follow this pattern. Instead, it appears to remain evenly spread across space, regardless of where matter is concentrated. Whether in the heart of a galaxy cluster or inside a vast cosmic void, its influence seems consistent. This uniformity is both helpful and puzzling. It is helpful because it simplifies how dark energy is included in cosmological models. A constant, evenly distributed component is much easier to work with mathematically than something that varies from place to place. But it is puzzling because most physical substances do not behave this way. Almost everything we know tends to clump, flow, or interact with its environment in some measurable way. Dark energy appears unusually indifferent to the structure of the universe around it. Another layer of mystery comes from its timing. For much of cosmic history, dark energy seems to have played a minor role. In the early universe, matter and radiation dominated the dynamics of expansion. Gravity shaped the formation of the first structures, pulling matter into the beginnings of galaxies and clusters. Only later, as the universe expanded and matter became more diluted, did dark energy begin to take on a dominant role. This raises an important question. Why now? Why does dark energy appear to become significant in the current era of cosmic history, rather than at the beginning or far in the future? From a purely physical perspective, there is nothing obviously special about the present moment in the universe. Galaxies, stars, and observers exist now. But the laws of physics do not seem to favor this particular time. Yet the influence of dark energy becomes noticeable precisely when matter becomes thinly spread enough for it to matter. Some scientists see this as a coincidence. Others view it as a clue. The so-called coincidence problem asks why the densities of matter and dark energy are of the same order of magnitude in the present epoch, even though they evolve very differently over time. Matter becomes diluted as the universe expands, while dark energy appears to remain nearly constant. These two behaviors should naturally drift far apart across cosmic history, yet for a brief window in time, they appear surprisingly comparable. This coincidence may simply reflect the fact that observers can only exist during a certain phase of the universe. Stars must form, heavy elements must be created, and stable planetary systems must develop. This requires time. By the time intelligent observers appear, the universe may already be entering the era where dark energy begins to dominate. In this sense, the timing may not be surprising at all. It may simply reflect the conditions necessary for observation itself. Still, the deeper question remains unanswered. What exactly is dark energy? The simplest models treat it as a constant property of space. More complex models suggest it could evolve over time, possibly linked to unknown fields or forces that permeate the universe. Some ideas propose that dark energy might be connected to modifications of gravity itself, meaning that what we interpret as a new component could actually be a sign that our understanding of gravity is incomplete on cosmic scales. Each of these possibilities has strengths and weaknesses. The cosmological constant model fits current data extremely well, but struggles with theoretical predictions from quantum physics. Dynamic models offer more flexibility, but introduce additional complexity and parameters that are difficult to test. Modified gravity theories attempt to explain acceleration without introducing a new energy component. But they must also match the many successes of general relativity, which has been tested with extraordinary precision. This situation is common in science at the frontier of knowledge, when observations extend beyond current explanations. Multiple competing ideas emerge. Each attempts to fill the gap in understanding, and each must survive increasingly precise tests. Over time, most ideas are refined or discarded, while a few gradually converge toward a more accurate description of reality. What makes dark energy particularly challenging is the scale on which it operates. It cannot be studied in a laboratory. It cannot be recreated in an experiment. It reveals itself only through the expansion of the entire universe. This means that every test relies on observing vast regions of space and interpreting light that has traveled for billions of years. The data is rich, but it is also indirect, making the process of interpretation especially delicate. Despite these challenges, progress continues. New surveys map millions of galaxies, creating detailed three-dimensional maps of the cosmic web. Space telescopes observe distant supernovae with increasing precision. Measurements of the cosmic microwave background provide snapshots of the early universe, offering clues about how expansion evolved over time. Each new dataset adds another piece to the puzzle. And yet, even as data improves, the core mystery remains unchanged. The universe is expanding, and that expansion is accelerating. Something is driving this behavior across the largest scales imaginable. Whether that something is a property of space, a new field, or a sign of deeper gravitational physics is still unknown. In the quietest sense, dark energy represents a reminder of how much of reality still lies beyond current understanding. The universe is not fully mapped, not fully explained, and not fully contained within existing theories. It continues to reveal new layers of complexity as observation becomes more precise. Somewhere within the vast expansion of space, within the nearly uniform darkness between galaxies, the answer is already present. It is simply not yet understood. Dark energy cannot be collected in a container, placed beneath a microscope, or examined inside a laboratory. There is no detector that flashes whenever dark energy passes nearby, and no spacecraft has ever traveled through a region where it suddenly became visible. Unlike planets, stars, or even invisible particles that occasionally leave measurable traces, dark energy reveals itself only through its influence on the universe as a whole. Because of this, astronomers have learned to observe it indirectly. This approach is common throughout science. Many important discoveries begin not by seeing something directly, but by carefully studying the effects it produces. Wind itself is invisible, yet moving leaves reveal its presence. Gravity cannot be seen, yet falling objects demonstrate that it exists. In the same way, dark energy is inferred from the slow and steady changes it causes in the expansion of the universe. The most important requirement for studying dark energy is patience. The universe changes at an incredibly slow pace. During a human lifetime, the expansion of space changes by such a tiny amount that no individual could ever notice it. Even civilizations lasting thousands of years would witness almost no visible difference in the arrangement of distant galaxies. The acceleration of the universe only becomes apparent when comparing light that has traveled for billions of years. Astronomers therefore transform distance into time. Every distant galaxy is also a glimpse into an earlier era of cosmic history. A galaxy located 1 billion light-years away is observed as it existed 1 billion years ago. Another galaxy 10 billion light-years away reveals conditions from a much younger universe. By observing galaxies across a wide range of distances, astronomers effectively build a timeline stretching across most of cosmic history. This timeline allows researchers to ask a remarkable question. How has the expansion of the universe changed from one era to another? Answering this question requires enormous surveys of the sky. Modern observatories no longer examine only a handful of galaxies. Instead, they observe millions of them. Powerful digital cameras attached to large telescopes capture enormous sections of the night sky in extraordinary detail. Specialized computers then identify galaxies, measure their positions, estimate their distances, and determine how much their light has been shifted toward the red end of the spectrum. The result is something extraordinary. Instead of a simple photograph, astronomers create three-dimensional maps of the universe. Imagine flying above a vast forest. Looking straight downward produces a beautiful picture, but it remains flat. Now imagine knowing the height of every tree as well. Suddenly, the forest becomes a fully three-dimensional landscape rather than a simple image. Galaxy surveys achieve something similar. Each galaxy is assigned not only a position across the sky, but also an estimated distance from Earth. Gradually, millions of points combine into enormous three-dimensional maps extending across billions of light years. Within these maps, astronomers search for subtle patterns. Galaxies are not distributed randomly. They form clusters, filaments, and enormous voids that together create the cosmic web. The exact arrangement of these structures depends upon how the universe expanded throughout its history. By comparing observations with theoretical predictions, scientists can determine which models best describe reality. One particularly valuable feature within these maps acts almost like a cosmic measuring stick. In the early universe, tiny pressure waves traveled through the hot plasma that filled space shortly after the beginning of cosmic history. As the universe cooled, those waves left behind a characteristic separation between galaxies. Billions of years later, astronomers can still detect this preferred scale within the distribution of galaxies. Because the original size of this pattern is understood, it functions as a standard ruler. Just as an architect might use a measuring tape to determine the dimensions of a building, cosmologists use this ancient cosmic ruler to measure how the universe has expanded over time. The larger the apparent ruler becomes, the more space has stretched since the light began its journey. This method provides an independent way of studying dark energy, separate from observations of exploding stars. When different techniques agree, confidence in the conclusions becomes much stronger. Another powerful source of information comes from the oldest light in existence. Long before stars and galaxies filled the universe, space was occupied by a hot, glowing plasma. As the universe expanded and cooled, light was finally able to travel freely in every direction. That ancient radiation continues moving through space today, filling the observable universe with an incredibly faint microwave glow. Although this light has traveled for nearly the entire history of the cosmos, it still carries tiny variations in temperature and density. These subtle patterns reveal what the universe looked like when it was only a small fraction of its present age. By comparing that ancient snapshot with today's universe, astronomers can determine how cosmic expansion unfolded across billions of years. Dark energy leaves its fingerprints within this comparison, influencing the overall geometry and evolution of the cosmos. Modern observations also rely heavily on computers. The amount of information collected by today's telescopes is almost beyond imagination. A single astronomical survey may record billions of individual objects. Processing such enormous data sets requires sophisticated software capable of recognizing galaxies, correcting observational effects, and comparing the results with detailed theoretical models. Supercomputers simulate entire universes, beginning with conditions similar to those of the early cosmos. These simulations allow gravity to shape galaxies and clusters over billions of years. Different amounts of dark energy produce different cosmic histories. Researchers then compare these simulated universes with the real one, gradually narrowing the range of possibilities. Despite all this technological sophistication, the actual observations remain surprisingly peaceful. Night after night, telescopes quietly collect faint light from galaxies so distant that their photons began traveling toward Earth long before human civilization existed. Every image represents ancient history, arriving in the present moment. Every spectrum contains information that has crossed unimaginable distances without interruption. There is something deeply calming about this process. No single observation reveals the answer. No single telescope solves the mystery. Instead, understanding grows almost imperceptibly, one galaxy at a time, one measurement at a time, one generation of astronomers after another, across mountaintop observatories, remote deserts, and silent spacecraft drifting above Earth's atmosphere. Humanity continues assembling an increasingly detailed portrait of the expanding universe. Each observation refines the picture, making the mystery of dark energy a little clearer while also revealing how much remains unknown. The universe has been telling its story through light for billions of years. Astronomers simply listen carefully, collecting those ancient messages one photon at a time, allowing the quiet expansion of space to reveal itself through the patient language of observation. The universe is constantly sending light toward Earth. Every second, countless photons arrive after journeys that began nearby or billions of light years away. Some left neighboring stars only a few years ago. Others started traveling long before the Earth had formed its oceans, before the first continents existed, and before life had appeared on our planet. Every beam of light carries information from a different moment in cosmic history, quietly crossing the darkness until it reaches a telescope. For centuries, all astronomical observations were made from the ground. Early astronomers looked upward with their eyes alone, carefully recording the movements of stars and planets. Later, larger and more sophisticated telescopes revealed moons, nebulae, galaxies, and distant clusters. These observatories transformed humanity's understanding of the cosmos, but they all shared one unavoidable limitation. They observed the universe through Earth's atmosphere. The atmosphere is essential for life. It provides breathable air, shields the planet from harmful radiation, and burns up countless small meteoroids before they can reach the surface. Yet for astronomers, the atmosphere also acts like an imperfect window. As starlight enters the atmosphere, it passes through layers of air that are constantly moving. Warm air rises, cooler air sinks, and gentle winds create tiny changes in density. These constantly shifting currents bend light ever so slightly, causing stars to twinkle. While beautiful to the eye, this effect blurs astronomical images, making distant galaxies appear slightly less sharp than they truly are. The atmosphere also blocks many kinds of light completely. Human eyes detect only a small portion of the electromagnetic spectrum. Beyond visible light lie radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Each reveals different aspects of the universe. Some show cool clouds of dust where new stars are forming. Others reveal extremely energetic events near black holes. Many of these wavelengths cannot pass through Earth's atmosphere, making them impossible to observe from the ground. To overcome these limitations, astronomers eventually carried their telescopes into space. Above the atmosphere, the universe becomes astonishingly clear. There is no air to blur incoming light. No clouds interrupt observations. Day and night no longer matter in the same way, because a telescope can continuously observe distant objects as it orbits the Earth or travels even farther into space. This new perspective transformed astronomy. Space telescopes began capturing galaxies with extraordinary detail, revealing structures too faint and distant for previous generations to observe. Tiny points of light that once seemed insignificant became recognizable as entire galaxies containing hundreds of billions of stars. Looking deeper into space also meant looking farther back in time, allowing astronomers to observe galaxies as they existed only a few 100 million years after the beginning of cosmic history. For researchers studying dark energy, these observations are especially valuable. The farther away a galaxy lies, the earlier it appears in the history of the universe. By observing galaxies from many different eras, Astronomers can reconstruct how cosmic expansion has changed over billions of years. Every new observation extends this timeline, making it possible to test whether dark energy has remained constant or behaved differently in the distant past. Space telescopes also observe enormous numbers of galaxies simultaneously, instead of studying only one small region. Modern surveys carefully scan vast portions of the sky, recording millions of galaxies with remarkable precision. Every image becomes part of an immense cosmic map. Distances, shapes, brightness, and positions are measured with extraordinary care, creating datasets so large that they require years to analyze completely. One subtle effect has become particularly important. As the light travels toward Earth, it passes countless galaxies and clusters. Their gravity gently bends the path of that light, slightly distorting the appearance of even more distant galaxies behind them. This phenomenon is known as gravitational lensing. Most of these distortions are incredibly small. An individual galaxy may appear only slightly stretched or tilted. No human eye could recognize the effect by casually looking at a single image. However, when millions of galaxies are studied together, a delicate pattern emerges. These tiny distortions reveal how matter is distributed throughout the universe. Since dark energy influences how large structures grow over time, careful measurements of gravitational lensing provide another indirect way of studying its effects. Researchers compare the observed patterns with detailed computer models, gradually refining their understanding of how the universe has evolved. Future space missions promise even greater precision. New observatories are being designed to map larger regions of the universe than ever before. They will observe billions of galaxies, extending humanity's cosmic census deeper into space and farther into the past. Every improvement in sensitivity allows fainter galaxies to be detected. Every increase in precision reduces uncertainty in the measurements. Some missions will concentrate on visible light. Others will specialize in infrared observations, allowing astronomers to study galaxies whose light has been stretched by billions of years of cosmic expansion. Still others will combine multiple wavelengths, creating a richer picture of the universe than any single instrument could achieve alone. These observatories are not searching for dramatic explosions or unexpected flashes. Instead, they patiently measure tiny differences. A galaxy that appears slightly farther away than expected. A cluster whose shape is subtly altered. A faint distortion repeated millions of times across the sky. Dark energy hides within these almost imperceptible details. Modern astronomy therefore depends not only on powerful telescopes, but also on extraordinary precision. Instruments must remain stable for years. Mirrors must preserve their shape with incredible accuracy. Detectors must record the arrival of individual photons while introducing as little noise as possible. Even the smallest imperfections can influence measurements when studying the expansion of the entire universe. Behind every beautiful astronomical image lies an enormous amount of careful engineering. Thousands of scientists, engineers, mathematicians, and technicians contribute to a single mission. Some design mirrors polished to astonishing smoothness. Others create detectors capable of recording unimaginably faint light. Others develop computer algorithms that transform raw observations into accurate measurements of galaxies billions of light years away. Together, these efforts allow humanity to observe a universe that previous generations could scarcely imagine. Every new telescope extends our vision. Every new survey enlarges our map. Every new observation adds another quiet piece to the story of cosmic expansion. Perhaps one day, among the countless galaxies recorded by future observatories, a subtle pattern will emerge that finally explains the true nature of dark energy. Or perhaps the mystery will deepen, revealing that the universe is even stranger than current theories suggest. For now, the great observatories continue their silent work above the atmosphere, patiently collecting ancient light that has crossed billions of years of space. They do not hurry. They simply watch, night after night, photon after photon, gradually revealing the history of an expanding universe whose greatest mystery may still be waiting just beyond the edge of present understanding. One of the oldest questions ever asked is also one of the largest. Does the universe have an edge, or does it continue forever? It is a question that has fascinated philosophers, astronomers, and curious minds for thousands of years. Even today, despite remarkable advances in modern cosmology, the complete answer remains unknown. Yet by studying the expansion of the universe and the influence of dark energy, scientists have learned a great deal about the possible shape and ultimate destiny of the cosmos. When people imagine the universe, they often picture a giant empty box filled with stars and galaxies. In this picture, it seems natural to ask what lies outside the box. If the universe has an edge, what exists beyond it? If it does not have an edge, how can something continue forever? Modern cosmology approaches these questions differently. The universe is not necessarily expanding into some larger empty space. Instead, space itself is expanding. This means that asking what lies outside the universe may not have a meaningful answer in the ordinary sense. Just as there is no location north of the North Pole on Earth, there may be no physical place outside the universe into which it expands. This idea is difficult to imagine because every experience in daily life involves objects existing inside larger surroundings. A house stands inside a neighborhood. A city exists within a country. A planet travels through space. The universe, however, contains all of space itself. There is no obvious larger environment beyond it that has ever been observed. To understand the possible shapes of the universe, astronomers often begin with simple geometric ideas. Imagine drawing two perfectly straight lines on a flat sheet of paper. They remain parallel forever, never meeting. This is the familiar geometry taught in school. Now imagine drawing similar lines on the surface of a globe. Although they begin parallel near the equator, they slowly move closer together until they eventually meet at one of the poles. The surface itself changes the behavior of the lines. There is also another possibility. Imagine a saddle-shaped surface. Here, straight paths gradually move farther apart than they would on a flat plane. Again, the geometry of the surface determines how objects travel. These examples involve two-dimensional surfaces, but astronomers apply similar ideas to the three-dimensional universe. The universe could possess positive curvature, somewhat analogous to the surface of a sphere. It could possess zero curvature, meaning that on the largest scales its geometry is essentially flat. Or it could possess negative curvature, resembling the geometry of a saddle. These possibilities may sound purely mathematical, yet they influence how light travels across billions of light years and how the universe evolves over cosmic time. Remarkably, modern observations suggest that the observable universe is extremely close to flat. This does not necessarily mean the universe extends infinitely. A flat universe can still have a finite size under certain conditions, nor does it rule out more complicated possibilities involving shapes that are difficult to visualize. It simply tells us that, within the limits of current observations, space appears remarkably close to having no overall curvature. Dark energy becomes especially important when considering the future. For much of the 20th century, scientists believed the amount of matter in the universe would determine its ultimate fate. If enough matter existed, gravity might eventually stop the expansion and reverse it. If too little matter existed, expansion would continue forever while gradually slowing. Dark energy changed this picture dramatically. Instead of gravity becoming increasingly dominant, dark energy appears to become more important as the universe grows larger. This happens because matter becomes more spread out as space expands. Galaxies drift farther apart, reducing the average density of matter across the universe. Dark energy, however, appears to remain almost unchanged even as more space comes into existence. As the universe grows, dark energy therefore becomes an increasingly significant part of the overall cosmic balance. Imagine two painters working on an enormous canvas. One paints using a fixed amount of color. As the canvas grows larger, the paint becomes thinner and more spread out. The other possesses a color that somehow remains equally vivid across every new section of canvas that appears. As the canvas continues expanding, the second painter gradually becomes more influential simply because the first painter's color becomes increasingly diluted. Matter behaves somewhat like the first painter. Dark energy behaves more like the second. This gradual shift has profound consequences. Current observations suggest that the expansion of the universe will continue accelerating for an extremely long time. Galaxies that are already distant today will slowly move even farther away. Light from many of them will require increasingly longer periods to reach us. Eventually, some galaxies may become so distant that the expanding space between us grows faster than their light can overcome. This idea may seem surprising, but it follows naturally from an accelerating universe. It does not mean those galaxies suddenly disappear. They continue existing exactly as before. Their stars continue shining. Planets continue orbiting. Entire civilizations, if any exist, would notice nothing unusual within their own galaxies. The change concerns the enormous distances between galaxies. As those distances grow, communication across the universe becomes increasingly difficult. Light requires longer journeys. Regions that are observable today may one day become permanently unreachable, not because they cease to exist, but because the expanding universe stretches the intervening space faster than light can bridge it. Fortunately, this process unfolds over unimaginably long periods. Nothing about daily life, Earth's future, or even the future of our galaxy depends upon these immense cosmic changes. The Milky Way remains securely bound together by gravity. Stars continue their ordinary lives. The solar system continues orbiting the center of the galaxy much as it has for billions of years. Dark energy quietly shapes only the largest scales of existence. This contrast is one of the most beautiful aspects of cosmology. On human scales, life continues almost completely unaffected. On cosmic scales, however, the universe slowly transforms. The great web of galaxies stretches. The vast voids become larger. Clusters drift farther apart with extraordinary patience. The process is so gradual that no single generation could ever witness it directly. Yet across tens of billions of years, the appearance of the universe changes profoundly. The night sky seen by distant future observers may contain far fewer galaxies than the sky visible today. Many of the magnificent structures currently filling deep astronomical images will have receded beyond observation, leaving each remaining galaxy increasingly isolated within an ever-expanding sea of space. Dark energy therefore influences not only the present universe, but also its far future. It quietly determines how the cosmos will continue evolving long after today's stars have exhausted their fuel, and long after the familiar constellations have disappeared. The shape of the universe and its ultimate destiny remain among the deepest questions in astronomy. Although many details are still uncertain, one conclusion grows clearer with every generation of observations. The universe is not standing still. It is gently unfolding, becoming larger, quieter, and more spacious with every passing moment, guided by a mysterious influence that continues to shape the grandest future imaginable. One of the most fascinating questions in modern cosmology is whether dark energy has always behaved exactly as it does today. Most current observations suggest that its influence has remained remarkably steady throughout much of cosmic history. This idea fits well with the simplest mathematical models, where dark energy is treated as a constant property of space itself. Yet simplicity does not necessarily guarantee truth. The universe has surprised astronomers many times before. And it is entirely possible that dark energy has its own long history, slowly evolving in ways that are only now beginning to reveal themselves. When scientists describe something as constant, they mean that its overall behavior remains unchanged over time. The speed of light in a vacuum is considered constant because careful measurements have always produced the same value. The electric charge of an electron appears constant for the same reason. If dark energy were truly constant, then every region of empty space throughout the observable universe would possess exactly the same amount of this mysterious energy, regardless of when or where it is observed. This picture is attractive because it is simple. Nature often follows elegant patterns, and the simplest explanation is usually the first one explored. If dark energy is constant, then many of the complicated equations describing cosmic expansion become easier to solve. Current observations also agree remarkably well with this idea. The expanding universe behaves almost exactly as such a model predicts. However, astronomers are careful not to confuse agreement with proof. Scientific models remain successful only until new evidence suggests otherwise. History is filled with theories that described observations extremely well for many years before eventually being replaced by even better explanations. This is not considered failure. It is simply how scientific understanding gradually improves. Suppose, for a moment, that dark energy is not perfectly constant. Imagine standing beside a river that appears completely calm. From a distance, the water seems to flow at exactly the same speed everywhere. Only after making careful measurements over many kilometers do you discover tiny variations. Some stretches move ever so slightly faster, while others slow almost imperceptibly. To an ordinary observer, the river still appears constant, but precise instruments reveal subtle changes hidden beneath its peaceful surface. Some scientists wonder whether dark energy behaves in a similar way. Perhaps its strength changes extremely slowly over billions of years. Such changes would be almost impossible to detect without extraordinarily accurate observations extending across enormous stretches of cosmic history. Even then, the differences might be so small that they remain hidden within the natural uncertainties of measurement. To explore this possibility, researchers have proposed several theoretical ideas. One suggestion is that dark energy may be connected to an invisible field filling the universe. A field is not a physical object like a planet or a cloud. Instead, it is something that assigns a value to every point in space. Familiar examples already exist in physics. The gravitational field describes how gravity acts throughout space. Magnetic fields surround magnets and influence charged particles. These fields cannot usually be seen directly, yet their effects are unmistakable. If dark energy arises from a similar cosmic field, that field might slowly change over time. Instead of remaining perfectly fixed, it could gradually evolve as the universe expands. Its energy might increase slightly, decrease slightly, or follow an even more complicated pattern. Such a field would still appear almost perfectly uniform across space, while changing only over immense periods far longer than any human civilization has existed. One popular family of ideas imagines a field that gently rolls through an invisible landscape of energy, almost like a ball moving across an enormous valley with an incredibly shallow slope. The motion would be extraordinarily slow, requiring billions of years to produce noticeable changes. During a single human lifetime, nothing would appear different. Even across millions of years, the change would remain almost impossible to detect. Only by comparing distant eras of cosmic history might astronomers eventually recognize its gradual evolution. If dark energy changes, even very slightly, the future of the universe could also change. A constant dark energy predicts one long-term future. A slowly weakening dark energy predicts another. A slowly strengthening dark energy suggests yet another possibility. These differences may not become important for tens or even hundreds of billions of years, but they demonstrate how closely the destiny of the universe depends upon understanding this mysterious phenomenon. Observational astronomers, therefore, search carefully for the smallest hints of change. Every new survey of distant galaxies provides another opportunity to compare different periods in cosmic history. Every precisely measured supernova contributes another point to the timeline of expansion. Every improvement in telescope technology reduces uncertainty just a little more, allowing scientists to test whether dark energy has remained truly constant or merely appears constant, because current measurements are not yet precise enough. So far, the evidence continues favoring remarkable stability. Within the limits of present observations, dark energy behaves almost exactly like a constant property of space itself. Yet, the phrase "within the limits of present observations" is important. Science rarely claims absolute certainty. Instead, it gradually narrows the range of possibilities as better data become available. Future generations of observatories may detect tiny departures from the current picture, or they may confirm the constant model with such extraordinary precision that alternative explanations become increasingly unlikely. Either outcome would represent important progress. If dark energy proves perfectly constant, then one of the simplest descriptions of the expanding universe becomes even stronger. If it changes, even slightly, then entirely new chapters of physics may open, revealing processes that current theories have only begun to imagine. There is something wonderfully patient about this search. Dark energy does not rush. If it evolves, it does so over billions of years. The universe itself becomes the laboratory, and cosmic history becomes the experiment. Instead of mixing chemicals inside glass containers or accelerating particles through underground tunnels, astronomers compare galaxies separated by unimaginable distances and ancient light that has traveled almost the entire age of the cosmos. Every observation is another quiet question posed to the universe. Has your mysterious expansion always been the same? Or have you been changing, slowly and silently, throughout the endless passage of cosmic time? For now, the universe answers with remarkable consistency but not complete certainty. Its expansion continues. Its galaxies drift farther apart. Its vast regions of empty space quietly grow larger. Whether this gentle acceleration represents an eternal constant or the slow evolution of something even deeper remains one of the most peaceful and enduring mysteries in all of cosmology.